Dear students, today we are going to study Bohr's correspondence principle. According to Bohr's third postulates, when an electron makes a transition from the inner orbit to the outer orbit or from the outer orbit to the inner orbit, then that electron should absorb or emit some energy. And this energy can be represented as h nu is equal to E2 minus E1, where E2 means it is the energy of the electron in the outer orbit and E1 is the energy of the electron in the inner orbit. From this equation, the frequency nu can be represented as E2 minus E1 divided by h, and this frequency is called Bohr frequency. And similarly, in the case of an electron which is orbiting around the nucleus, then the number of revolutions per second executed by that electron, it is called the orbital frequency and is represented by nu orbital. And this Bohr's correspondence principle relates these two frequencies, that is the Bohr frequency and the orbital frequency. The Bohr frequency means it's the frequency of the emitted radiation when an electron in an atom makes a transition from one energy state or from one orbit to another orbit. Then the orbital frequency means the frequency of the electron orbiting round the nucleus in an atom. This Bohr's correspondence principle, it correlates these two frequencies. അതായത് ഒരു ക്ലാസിക്കൽ തിയറി അനുസരിച്ചിട്ട് ഒരു ആക്സിലറേറ്റിംഗ് ചാർജ് ബോഡി അത് ഒരു ഇലക്ട്രോൺ ആണെങ്കിൽ, ഒരു ആറ്റത്തിന്റെ കേസിൽ ഒരു ഇലക്ട്രോൺ ആണെങ്കിൽ ആ ഇലക്ട്രോൺ കണ്ടിന്യൂസ്ലി എനർജി എമിറ്റ് ചെയ്യും. അതായത് ഒരു ഇലക്ട്രോൺ ഒരു ന്യൂക്ലിയസിന് ചുറ്റും റിവോൾവ് ചെയ്യുമ്പോൾ ഇറ്റ് ഷുഡ് എമിറ്റ് കണ്ടിന്യൂസ് എനർജി. അതേസമയം ക്വാണ്ടം തിയറി അനുസരിച്ച് ഒരു ഇലക്ട്രോൺ ഒരു ഓർബിറ്റിൽ നിന്നും മറ്റൊരു ഓർബിറ്റിലേക്ക് ട്രാൻസിഷൻ നടക്കുമ്പോൾ അത് എമിറ്റ് ചെയ്യുന്ന റേഡിയേഷൻ അതെന്ന് പറയുന്നത് കണ്ടിന്യൂസ് അല്ല, അത് ഡിസ്ക്രീറ്റ് ആയിരിക്കും. അതായത് പാക്കറ്റ്സ് ഓഫ് എനർജിയാണ്. എച്ച് ന്യൂവിന്റെ ഇന്റഗ്രൽ മൾട്ടിപ്ലൈറ്റാണ് അവിടെ എനർജി എമിറ്റ് ചെയ്യുകയും അബ്സോർവ് ചെയ്യുകയും ചെയ്യുന്നത്. അതുകൊണ്ട് തന്നെ ബോർ ഫ്രീക്വൻസി എന്നത് ക്വാണ്ടം തിയറിയുടെ ബേസിസിലും ഓർബിറ്റൽ ഫ്രീക്വൻസി എന്നത് ക്ലാസിക്കൽ തിയറിയുടെ ബേസിസിലും എക്സ്പ്ലെയിൻ ചെയ്യാം. Then in Bohr correspondence principle, it correlates or it establishes a relation between the classical frequency or the classical theory and the quantum theory. So according to Bohr principle, the higher the quantum number, the more nearly does the frequency of the emitted radiation for a transition from one orbit to the next below, that is the Bohr frequency. It approaches the frequency of the electron in the orbit, that is orbital frequency. That is the Bohr correspondence principle states that the higher the quantum number means the higher the value of the principal quantum number n, because the principal quantum number n represents the energy levels. That is, when the energy levels involved is very high, then the Bohr frequency, that is the frequency of the emitted radiation for a transition from one orbit to the next below. This Bohr frequency, it approaches the frequency of the electron in the orbit, or this can be represented as when the quantum number is involved is large, the Bohr frequency, it approaches the frequency which the atom would emit according to the classical theory. That is, the Bohr correspondence principle can be stated in two different ways. That is, when the quantum number involved is large, the Bohr frequency approaches the frequency which the atom would emit according to classical theory. That is, the Bohr correspondence principle establishes a correlation between the results obtained from classical and quantum theories. That is, the Bohr postulates can be stated as when the quantum number involved is very large, then the Bohr frequency approaches the frequency which the atom would emit according to classical theory. And for deriving this correspondence principle, we are considering the radius of the nth orbit. We have already studied the equation for the radius of the nth orbit as Rn is equal to n square h divided by 2 pi mc alpha. That is, Rn is equal to n square h divided by 2 pi mc alpha, where n is the principal quantum number and h is the Planck's constant and m is the mass of the electron and c is the velocity of light and alpha is the fine structure constant. And this alpha can be represented as alpha is equal to e square divided by 4 pi epsilon 0 hc divided by 2 pi. This is alpha and it is called fine structure constant. The velocity of the electron in the nth orbit is given by v is equal to c by n into alpha, where alpha is the fine structure constant and c is the velocity of light and n is the principal quantum number or the orbit in which the electron belongs. That is, for the first orbit n is equal to 1. Then the period of revolution of the electron in the nth orbit is given by the period t can be represented as t is equal to 2 pi by omega. We have already studied the relation between the period t and the angular frequency omega. That is, t is equal to 2 pi by omega. But omega can be written as omega is equal to v by r, where v is the velocity of the electron and r is the radius of the orbit. If we are considering the period of revolution in the nth orbit, then t can be represented as 2 pi divided by omega means v by r. For the nth orbit, it will be vn divided by rn. That is, vn divided by rn. That is, the period of revolution of the electron in the nth orbit is given by t is equal to 2 pi rn divided by vn. Therefore, the orbital frequency new orbital can be represented as 1 by t. Frequency and period are inversely related. It can be written as t is equal to 2 pi rn by vn. Therefore, 1 by t is equal to vn divided by 2 pi rn. But we know that vn is equal to c by n into alpha. Therefore, c by n into alpha vn into 1 by 2 pi rn. But rn is equal to n square h divided by 2 pi mc alpha. That is, on rearranging we get m c square alpha square divided by n cube h. This is orbital frequency new orbit. Then the energy of the nth orbit is given by E is equal to minus half m c square alpha square by n square. We have already studied the equation for the energy of the electron in the nth orbit as E is equal to minus half mc square alpha square by n square. And the Bohr frequency when a transition takes place from an orbit of quantum number n to an orbit of quantum number n1. That is, considering different orbits. Considering an outer orbit having quantum number n to an inner orbit having quantum number n1. Then the energy will be emitted and the frequency of this emitted radiation, it can be represented as new Bohr is equal to En minus En1 divided by h. And E can be represented as minus half mc square alpha square by n square. Therefore, En can be represented as minus half mc square alpha square divided by n square h minus half m c square alpha square divided by n1 square h. This is the expression for Bohr frequency. On rearranging we get, and the second term is minus of minus, therefore it will be plus and it can be taken as the first term. And considering the common terms, that is m c square alpha square divided by 2h as common, and the remaining term will be 1 by n1 square minus 1 by n square. That is, this can be written as m c square alpha square by 2h into, the denominator will be n1 square n square, the numerator will be n square minus n1 square, and thus Bohr frequency nu Bohr is equal to m c square alpha square by 2h into n square minus n1 square minus divided by n1 square n square. Therefore, the ratio of the frequencies, orbital frequency divided by Bohr frequency, it can be written as, that is m c square alpha square divided by n cube h into 2h n1 square n square divided by n square minus n1 square m c square alpha square. And on rearranging we get 2 n1 square n square divided by n cube n plus n1 into n minus n1. That is, n square minus n1 square can be written as in the form a square minus b square. A square minus b square will be a plus b into a minus b. Similarly, n square minus n1 square is n plus n1 into n minus n1. Therefore, this ratio will be 2 n1 square n square divided by n cube into n plus n1 into n minus n1. And when n and n1 are large, that is when the quantum number involved is large, that is n means the quantum number, that is when n and n1 are large, then n minus n1 is equal to 1. That is, here the n minus n1, it will be 1. It can be taken as 1. Then n1 square n square approximately equal to n raised to 4. That is n1 square n square, it can be approximately equal to n raised to 4. And n plus n1 can be equated to 2n. That is, when n and n1 are large, then n minus n1 is equal to 1 and n plus n1 is 2n, and n1 square n square is n raised to 4. So making these approximations in the equation, then we get the orbital frequency divided by Bohr frequency is equal to 2n raised to 4 divided by n cube into 2n into 1, and this will give 1. That is, the ratio of the orbital frequency to Bohr frequency is 1. That is, the orbital frequency approaches the Bohr frequency when the quantum number is large. And this was pointed by Bohr in 1923 and is known as the Bohr's correspondence principle. That is, the Bohr's correspondence principle states that when the quantum number involved is large, the Bohr frequency approaches the frequency of the electron in the orbit. That is, the ratio of the orbital frequency to Bohr frequency is equal to 1. And this is Bohr's correspondence principle.